1800 years ago, someone carved two characters above a stone doorway, Wen Jai, meaning warm house. Modern sensors proved them right. Through an entire winter, this limestone structure held a steady 19 degrees Celsius. No furnace, no electricity, 75% less energy than the home next door. Its walls work like a heat battery that never runs out. So the real question is not whether this design works. It is why we abandoned it. Every material handles heat in its own way, but stone stands apart for its ability to store warmth deep within its mass. The science behind this goes by the name thermal mass. In simple terms, thermal mass is how much heat a material can soak up, hold, and then slowly give back to its surroundings. This is measured using numbers like density, specific heat, and thermal conductivity. Limestone, the main ingredient of the Longmen House walls, is especially good at this. A cubic meter of local limestone weighs 2,650 kilograms. Its specific heat, the amount of energy needed to raise 1 kilogram by 1 degree Celsius, is roughly 0.91 kilojoules per kilogram per degree Celsius. Multiply these together, and you get a volumetric heat capacity of around 2.4 million joules per cubic meter per degree Celsius. That means each cubic meter of wall can hold almost the same amount of energy as 70 liters of boiling water cooling to room temperature. But storing heat is only half the story. The other key is how slowly that heat moves through the stone. Limestone's thermal conductivity is about 2.5 watts per meter per degree Celsius. That is much lower than metals, but higher than modern insulation. The result is a slow, steady flow of warmth from the outer layers toward the inside. In a wall nearly 3/4 of a meter thick, it can take hours for heat absorbed during the day to reach the interior surface. This delay is called thermal lag. It is the reason the house stays warm long after sunset, smoothing out the sharp ups and downs of outdoor temperatures. This combination of high heat capacity and slow conductivity turns the walls into a kind of natural battery. They soak up energy from sunlight, cooking fires, and even people's daily activities, then release it back into the rooms over many hours. The effect is not just comfort, but stability, a steady indoor climate, even as the world outside swings from freezing nights to chilly days. These are not abstract numbers. They are the hidden physics that made the ancient warm house inscription a reality. On a limestone ridge at 30 degrees 54 minutes 12 seconds north, 103 degrees 34 minutes 45 seconds east, the Longmen stone dwelling stands as more than a relic. Every line and angle of this house reveals a clear, intentional response to climate. The walls, built from local limestone blocks and packed river gravel, reach up to 84 centimeters thick, far beyond what was common for ordinary homes of the era. Their mass was not just about strength, but about harnessing the physics of heat. The house's long axis is set 12 degrees east of true south. This subtle rotation is no accident. It ensures the facade catches the low winter sun for as many hours as possible, maximizing solar gain during the coldest months. Narrow vertical slits, each about 1 meter high and 30 centimeters wide, are cut into the southern face. Instead of glass, these openings are covered with thin sheets of mica, translucent and durable, able to diffuse sunlight while cutting down heat loss. Archaeological analysis shows this mica glazing let in only about 15% of the sun's energy, but kept out far more cold than open windows ever could. At the heart of the house sits a central hearth, surrounded by antechambers that channel warm air through the core. Niches in the east and west walls hold firewood, letting the stone absorb heat from daily cooking and gathering. Overhanging eaves shade the stone in summer, but let winter sunlight strike the wall directly. On one lintel, carved in bold seal script, an inscription reads, "Warm House." Nearby, a bronze tablet invokes the god of the southern sun. These are not decorative flourishes. They are records of intent, proof that the builders understood the link between sunlight, stone, and comfort. Dr. Li Wei, who led the excavation in 2004, points to these features as evidence that climate-responsive design was no accident, but a deliberate choice encoded in both architecture and culture. Inside a climate-controlled laboratory, a team led by Dr. Sofia Romano set out to put the ancient stone house theory to the test. They built a scale mock-up chamber, matching the limestone wall thickness, gravel core, and mica-glazed windows of the Longmen dwelling. The setup was rigged with precision sensors, thermocouples embedded at different wall depths, data loggers tracking air and surface temperatures, and a calibrated solar simulator mimicking winter sun. Each day, the chamber absorbed 4 hours of simulated sunlight, followed by a 12-hour chill that dropped the exterior to near freezing. The results came in as a string of numbers, but their meaning was clear. The thick limestone walls didn't just slow the flow of heat, they stretched it out over time. Internal wall temperatures peaked nearly 6 hours after the sun's rays hit their maximum, a thermal lag of 5.8 hours. Even as the outside temperature plunged, the interior air swung by only 2 degrees Celsius from its daily high to low. Throughout the cycle, the space stayed 8 degrees warmer than the outdoor minimum, with no mechanical heat source. To verify these findings, Dr. Romano's team ran Energy Plus simulations, inputting the exact material properties measured in the lab. The model predicted a 70% cut in heating energy compared to a modern lightweight building in the same climate. These numbers weren't just theoretical. The sensors and simulations told the same story. High thermal mass, slow conductivity, and careful orientation allowed the ancient house to ride out winter cold on stored warmth alone. The lab results gave hard proof that centuries of lived experience had already shown on the ridge at Longmen. Winter in the Sichuan foothills can be unforgiving, but inside the Jiang family's reconstructed Longmen house, the story plays out differently. Over the winter, from 2019 to 2020, a small digital logger tucked in the living room quietly tracked the air temperature every 10 minutes. The numbers, plotted across 3 months, told a steady tale, an average of 19.2 degrees Celsius indoors, even as the world outside dipped below freezing. Most days, the house coasted on stored warmth alone. Only during a 3-day cold snap, when the mercury plunged to -5, did the family light their compact biomass stove. They counted just 12 hours of supplemental heating for the entire season. Their electricity bill for heating came to the equivalent of 560 yuan, compared to 2,300 yuan for neighbors in conventional homes relying on electric heaters. That is a 75% savings year after year. But the numbers only hint at the lived experience. The Jiangs describe mornings without the shock of cold floors, afternoons of gentle, even warmth, and evenings where the air stays still, no fans, no forced air, no dust swirling through vents. The thick limestone walls mute the noise from the lane outside, creating a quiet that feels rare in modern life. The family notes that the air is less dry than in homes with central heating, though they do open windows regularly to manage moisture. For the Jiangs, comfort is not just a number on a thermostat. It is the feeling of walking barefoot in January or gathering around the hearth without worrying about drafts. Living in a house that mirrors the choices of ancient builders, orientation, mass, and material has become a daily connection to the past. Their story turns the data from charts and models into something tangible, a home that works with the seasons, not against them. By the mid-1800s, the rules of building began to change. Manuals like the Builder's Handbook from 1853 promoted thin brick walls, just 15 centimeters thick, over heavy masonry. The logic was simple. Thin walls meant faster construction and lower costs. In 1862, a clause in the British Housing Act set a standard wall thickness for urban homes, arguing that thinner walls reduced fire risk and made it easier to heat buildings with new coal-fired furnaces. At the same time, inventors raced to patent iron frame construction and steam boilers, shifting the focus from passive warmth to mechanical heating. Companies tied to coal and iron lobbied for these changes, pushing building codes and public opinion away from thick, heat-storing stone. The result was a new normal: lightweight walls, rapid urban growth, and homes that now relied on machines instead of the slow, steady comfort of thermal mass. Thick stone walls may have stood the test of time, but today, rules and regulations block their return. Modern building codes, like the 1998 National Building Code, set a 40-centimeter cap on exterior masonry unless special engineering is approved, a fraction of the mass found in historic dwellings. After the 1973 oil crisis, utility companies circulated memos urging a shift to electric heating, arguing that old-fashioned stone homes would slow the push for grid power. Mortgage lenders, focused on cost per square meter and rapid completion, often reject thick wall projects as too slow and expensive. Insurance companies add another hurdle by charging higher premiums for massive masonry, citing increased seismic risk. Even when the science is clear, these institutional barriers make it nearly impossible to build homes that store heat the way ancient stone houses once did. Today, buildings account for nearly 40% of global energy use, much of it just to keep us warm. As extreme weather grows more common, ancient lessons in thermal mass and passive design offer real solutions. Sometimes, the most advanced ideas are the ones we nearly forgot. What would you bring back?